Without further ado, we'll carry on here, and our next speaker is Weishi Wang, who will tell us about Quiqbox v0.6, basis design for electronic structure and beyond.
Okay, hello everyone. My name is Weishi Wang. I'm a PhD student in the Department of Physics and Astronomy at Dartmouth College. Today I'm very happy to talk about some progress of a very, I would say, unpopular and small package I've developed in the past few years. It's called Quiqbox. And my title is Quiqbox 0.6, basis design for electronic structure and beyond. So I think my talk will basically organize into three parts. I will try to answer three questions. The first question is that, okay, why did we develop Quiqbox? So to answer that, we need to ask more questions. That's how you do scientists, right? First, why do we care about basis set? And then what can the previous version, Quiqbox 0.5, do or cannot do? And the second part is the meat of the talk, which is what's new in Quiqbox 0.6. So specifically, I will talk about three main parts: new parameterization system, new basis construction system, and new computation pipeline. And the last part, I would like to ask this question: what is Quiqbox if not a basis set generator? So typically, when you ask what is something if not something, you are saying it's definitely only that thing. But here, I want to take it literally. So to answer this question, I hope that I can show that maybe Quiqbox is not only useful for basis set design. Maybe it can be useful for some other, I think, scientists for some other purpose. And why that can happen, I will explain later. Okay, so I think since I'm in computational chemistry and material science, I don't need to explain too much about this. So basically, the subject of problem we're studying is electronic structure. And we have some electronic Hamiltonians. It's written in the first quantization. And then you will do basis set discretization to discretize to get those like one-body integrals and two-body integrals. And then, so here, when we actually discretize, we assume that normally we assume it's orthonormal orbitals. And then those orbitals can also be linear combinations of what we call basis functions. And those basis functions need not to be orthonormal with each other, so they will have some what is called an overlap matrix. And then after you discretize your Hamiltonian, and then you can have some eigenstate approximation. We know that the most basic one is the mean field approximation, like Hartree-Fock. And after that, we can apply other, more advanced algorithms. And then when you have some ansatz, you still need to solve them, right? So there are different ways to solve them. But if we look at this pipeline from a basis set researcher perspective, I would say that the really quantified problem that we're trying to study is actually a coupled one. Is what we study is always not entirely what nature provides us with, is actually under this discretization of basis set. So if we look at that, we can see that basis set is actually not only just a preprocess, but it also is an encoding method. It can actually both affect how we describe the target Hamiltonian, and also it might also affect the downstream accuracy or like complexity for the eigensolver. So here, basically, basis set can encode the information, and it can also affect the performance. So okay, so I personally am also from a quantum info perspective. So one thing we really care about is that, okay, can we simulate molecular materials on quantum computers? So we know that in traditional computational chemistry, you will have very accurate method nowadays with either DFT or couple cluster. But when you look at those quantum algorithms, okay, one thing I noticed that, okay, why are people just using SU3G? For any people who do quantum chemistry, traditionally you will know that it's giving you not very accurate result, right? So it turned out that the reason for that is because our quantum devices are still very limited. Specifically, the number of qubits or high fidelity qubits on your quantum device is directly related to the size of your basis set. So as long as you go to a little bit larger basis set, then it will surpass the limit of your quantum device. So can we design or configure basis set for NISQ molecular simulation in a more systematic fashion? So NISQ here stands for noisy intermediate scale quantum. So it's the current state of our quantum device. So to kind of like embark on this journey, we basically started this idea to develop a package, which is the Quiqbox, and we also kind of like publish a technical paper about it back in 2023. So what does Quiqbox do? Or how can it actually help you design basis set? So basically, we are going for a multi-level construction procedure. So we know that for molecular system, typically we would use Gaussian-type orbitals. The most simple case is the primitive Gaussian-type orbitals. So you just have n here is the normalization constant, and then you have your Cartesian representation of your angular momentum part, and then you have the Gaussian to represent your radial part, right? And then secondly, you can do contraction because we know we have nuclear cusp and electron-electron cusp, and then you need actually the Slater type orbitals to describe them. So in order to mitigate that, we basically try to do this multi-concentric linear combinations of Gaussian type orbitals. And then the third level is that, okay, we can basically even take some mixture of different contracted Gaussian type orbital. So on this level, it's basically on the same level of our molecular orbitals in a traditional sense, right? So when we do a Hartree-Fock calculation, we basically do orbital rotations, and then we'll mix different basis functions with different subshells, right? I would argue that maybe a little bit different here is that in a traditional electron structure calculation, you always go full subshell, right? Because due to the iterative nature of your molecular integral calculation, you might as well just store all the angular momentums. But, okay, so all of those Quiqbox can do previously also, so what we add to that, like what new do we bring to the menu? So it's basically this level 4. It's called hidden layer mixed contracted Gaussian type orbitals. So we know that those Gaussian type orbitals, they have their parameters, right? Like the contraction coefficients, the exponent coefficients. Normally we calculate those based on atomic systems or some other methods, and then we just store them, we reuse them every time. But we're thinking that what if we can actually optimize those parameters? That would still be too many of them, right? Because you can have in order to have a high quality basis set, you will have so many basis functions, then that would be very costly. And for example, for exponent coefficients, they are nonlinear coefficients. That would be very hard to optimize them. So we need to find a way to be able to optimize those parameters while reducing the dimension of a parameter space. So we do that by introducing some hidden layer to correlate those parameters. So specifically, we have those what is called the primitive parameters, and then they can correlate with each other and then form what is called the contracted Gaussian type orbital parameters, and now they will form like basically a basis function, a basis set parameter. Okay, so this is basically a complete like electron structure computation graph when we're incorporating the construction of your basis set. So on the left part is basically you have some theta here. They are primitive basis set parameters, and then they can couple in some way and then become your orbital parameters, which are represented in P. And then you can use those parameters to build your contracted Gaussian type orbitals. And then you can further mix them to form your mixed contracted Gaussian type orbitals. And only then you have your basic basis set. But then different from the traditional sense, you have track of all those parameters. And then when you feed them into your whatever SCF algorithm or other algorithm to solve for example, ground state energy, you will be able to see the correlation between those parameters along with the coefficients of your eigensolver. So, and then we basically deploy this variational parameter optimization procedure, which is, okay, when we start with some fixed set of parameter values, and then we, for example, here I'm showing you just the simplest Hartree-Fock SCF solver, and then we solve it, and then we add a stationary point. At that point, we try to calculate the gradients of those parameters at that stationary point. And then we update our parameters, and then we do another round. So this iterative back and forth variational optimization actually has shown in the paper of our paper that can actually drastically improve some performance. Okay, so that's basically a recap of 0.5 if you're not familiar with the library. So what's new in 0.6? Okay, so if we look at 0.5's basis set system, basically we take the central idea of Gaussian type orbitals, and then we go two directions. One, we can basically have more ways to combine those Gaussian type orbitals, or the other way is that we can basically have finer control of the parameters living inside of those basis functions. So 0.6 also take further of those two directions. For the construction of your basis functions, we have updated basis construction system. Specifically, we can actually have what is called composable basis function operators. So basically, we can treat some basis functions as value elemental types, and then we can combine them together basically through an algebraic way. So for example, one example of that later on I'll show is basically how you can combine, radial part, like the Gaussian with some other part. And then we have linear combinations of mixed type basis functions. That means that, okay, in 0.6, if you want to go crazy, you say like, I don't want to just study Gaussian-type orbitals, you can technically define your own customized basis function. And then you can combine that with Gaussian-type orbitals. And then at last, we also implement this automatic orbital renormalization because they represent, single particle wave function. We want them to be normalized, and then the more complicated species you have for your basis function, it's harder to, have a, formula to automatically renormalize them. So we actually do that basically based on machinery. And then for the parameter side, we also have updated parameterization. So previously, I showed that we can have those correlations between those parameters, but that's limited to scalar and scalar correlation. But here, we can actually allow array type parameters. So we basically allow, you can have a parameter that themselves is basically array or vector. And then you can have tensor to tensor correlations. And then the one last thing I think is very interesting is called this dynamic graph connection. And I will talk about it later. So here, we actually try to show a demonstration of what I mean by array type parameter. So this is what I explained before. Whenever you have a parameter, those correlations, you can think of, and when they are basically inside of your computation graph, the parameter themselves, they're actually already forming a computation graph. And in machine learning community, they basically call this directly acyclic graphs. So essentially, what we're here doing is basically building those kind of graphs. So here is basically a new example in 0.6. Now you can have a primitive or starting nodes like the x1 and y1. x1 is a scalar and y1 is a vector, but then you can actually combine them together. So whenever you construct the x3, it's not just you are calculating the result value of x3. You are actually storing the whole information of this graph. So how is this done on a coding interface level? So here's a code snippet. Okay, you can use Quiqbox, and then you can define some. As you can see here, f1 is some mapping function. F2 is a mapping function. Those are just generic, function. It can be, from generic function with anonymous functions. And then you can define a first node. What we use here is a function called gen tensor var. So after you do that, you actually get this node x1 here. And then you can see that here is actually of type unit var. And then there's this kind of a double direction arrow here. It means that it basically is almost f is a primitive parameters. It has no dependency, and then it stores a value of 2.0. And then, but when you try to construct your x2 here, you actually use another constructor called gen cell param. And then it will give you a reduced param that only have one direction. So this means that itself is only just a mapping of its input to some output value. And here, because everything is stored, we're storing the structure of your computation graph instead of actually doing the calculation, so you can think of it as a lazy operation. So it actually does not, print out the result. You only get to know the result when you evaluate later. So you can do this iteratively, and then you basically get your result as x3. And then when you evaluate the x3 result, you basically just call it as if it's a function without any argument. And then you just get to evaluate the whole computation graph. It's just that easy. And then here I basically verify that, okay, compare the result of evaluating x3 with actually explicitly writing down those functions and then do this computation yourself. They actually match. And then the amazing part about this is that this graph, because it's constructed compositively, so basically each part of it is themselves a computational graph. It can be as simple as just a node or some subsequent stuff. So for example, for the 2.0 here, you can basically replace it with your x1 here, and then treat it as a function, and it will still basically evaluate x1's value and input that. Okay. This part, I would say, is still pretty, I think, similar to, just traditional, computation graph you constructed. But here, I think, is one thing that actually makes it more interesting is what we call a dynamic graph connectivity. So if you really think about the graph structure, I would consider there are like mainly three kind of like connection. So there's this one level is that if we consider x2, it's basically like a passing node. It has some input and it has some output. And then you have another level is that x2 becomes like just x1. It's just itself. It's a parameter, and then it provides some pre-stored value. And another one is that basically this x2 can no longer even change. It's basically just like a constant holder. It's like a cache. So in Quiqbox, basically it allows you to have those three levels for each node you constructed when you try to construct a parameter. So like an example here is that if we examine the screen level of x1, it's just 1 because it's basically at the beginning of your computation graph, and then it only feeds forward its value. So you can actually use this function setVal to change its value. And then after you change the value, you evaluate x3, which is the end node of your graph, the value will just dynamically change. So this means that you can dynamically change your graph. But what's more is that you can even now, okay, say if I want to change maybe some other stuff. Here is a typo. For example, I want to change x2, but it says like you cannot change it. The reason for that is because if you investigate the screen level of your x2, which here is a typo of x3, it will say that the screen level of it is 0. It means that itself is not some variable. It's really just a mapping relationship for its previous node. So how can you just directly assign a value to it, right? You cannot do that. But what you can do in Quiqbox is that you can set screen level. So basically, you can forcibly change x2 from just a simple mapping from its previous nodes to like as if it's an independent value itself. And after you do that, you can basically set its value. And then it will also affect downstream graphs. So that means that even after you create a graph, you can dynamically change the connectivity of your graph and change the value of it. And then I would say this kind of like inspires some very interesting use case for Quiqbox. There's also new custom basis customization system. So if we go back to this previous very rudimentary example, this primitive Gaussian-type orbitals, you can already see that it actually made of multiple parts, right? It has radial parts, and it also has the angular momentum part. So you can basically consider this as some very primitive function, core function. For example, here is just a Gaussian function. And then you apply some operator to it to actually modify it, to build a more composite basis function out of it. So by doing that, you can actually, Quiqbox actually allows the user to define their own core functions and apply some specific predefined operators in Quiqbox to construct new basis function. So one example for that is basically, for example, if you don't want to use Gaussian-type orbitals, you just want to use Slater-type orbitals, right? Now you just swap out the Gaussian function for the radial part and replace it with exponential, and then you still keep the angular momentum part, and then you can basically construct a Slater-type orbital for yourself. And one example here I showed is basically we try to do a basis function like flavor of mimicking the one-dimensional Coulomb interaction. We know like we cannot have analytical result for calculate a one-dimensional Coulomb integral, but we can actually use sums of Gaussians to actually approximate that. So here basically I construct just a user-defined function is a Gauss-Coulomb. And then I can basically take the linear combinations of them, and then that will give me better approximation of this 1 over r operator. But because like even though it's 1 over r approximation in one dimension, but it actually takes in the position of 2 coordinates, right? So if you look at this operator itself, it's almost as if itself is a 2-dimensional basis function, because it takes the x1, x2. And then in Quiqbox 0.6, you can literally treat this operator as if it's a basis function. And then here I can even calculate its overlap. So this is basically the powerful kind of like, I would say, combination between parameterization system and the basis construction system is that you can not only design your custom basis functions, but you can also just treat them as, just evaluate them. So you see like, okay, now we are doing a lot of custom stuff. But if we want to do realistic calculation, then what's the performance, right? We need to find a kind of like a manageable way to deal with this. So I admit that when I tried to develop those like features, I got a little bit taken away. So I really kind of got a headache to think about how can I deal with all of those. Thank you. So basically, what I do is that we have a new computation pipeline. So in order to do this, we have what is called a computation graph transpilation framework. So you start with what is called the param box framework. So in the previous example, when I show all those different parameters, and then you can couple them to form this computation graph, they're all considered parameter box. And then use those parameters, you can actually construct some field functions. The field functions, they basically take in some Cartesian coordinates, but they are not necessarily orbital because they might not be normalized. So you take them into the third step, which you actually confine them to be orbital, to be normalized, and then you kind of go backwards a little bit because for the orbital, we just want to represent what's the information stored at. But when you actually try to calculate the integral with them, some basis function or orbitals, they have analytical formula, right? So you can just basically, if they're just Gaussian-type orbital, you can just use those very mature molecular integral like algorithms. But what if they're not? Then you only can fall back to numerical integration. When you do numerical integration on those basis functions, you would need to make them just seem like generic functions. Because that's how we do numerical function anyway, right? You put in some integrand, and then you try to do the stuff. So this is basically what the step 4 going through this computation graph means, is that when you have an orbital, not only we can construct some orbitals, we can also deconstruct or decompose an orbital and then transpile them into a generic function. And then just this generic function, if you have analytical solution to calculate the integral with them, fine. If not, then we just plug them into numerical engine. And so far, we basically use this H-cubature adaptive quadrature engine for the integral calculation. Okay, so at this point, I basically show all the main features of Quiqbox. So we can finally arrive at the last question. So what is Quiqbox if not a basis set generator? Okay, so yeah, as you can see, I use a lot of green here because I'm from Dartmouth, but I use different shade greens as well, right? So if we look at the left side here, if I do this yellow circle here, you can see this part. If you just focus yourself on this left side and ignore the right side, this is pretty generic, right? It's almost as if it's not really related to any, electron structure or a basis set stuff. It's basically just I have some way to construct a very dynamic, graphs, directed graph structure, and then I can basically make some generic function out of it. So basically, what I realized is that after I have this system, maybe I can do something interesting with just this part beyond basis set. So here's one example. So we talk about we have doing some electronic structure solver. One very rudimentary one is SCF solver for restricted Hartree-Fock. What if we just run a differential Hartree-Fock and then we're not using those for example DIIS solvers, right? So this is an example. So we first use Quiqbox, of course, we need to calculate the necessary integrals of our target system. So forgive me for using hydrogen as a very simplistic example. I'm just trying to demonstrate, right? Okay, so here I'm calculating the overlap, and then also normalization matrix, and the one-body integrals, two-body integrals. And then, okay, here is basically, it's same as the example I showed before to construct a commutation graph, except this is just more particular. We're actually constructing the commutation graph of your restricted Hartree-Fock. And then here I'm basically just following literature here, but I just need to write a few lines of code as if your Hartree-Fock energy is some objective function. And then the result is basically another param box, is a parameter box, but itself, whenever you evaluate it, it will return the value of your Hartree-Fock energy with respect to the pre-stored coefficients. But here, another very interesting function is called param graph caller. So this basically is the transpilation process I mentioned before. It will basically transpile this parameter box into a generic function. And then you can even investigate the parameter of this generic function. It's basically stored in this property source, and then you can obtain to get the value of it. And then here, I'm actually working with like other libraries. So it's not like Quiqbox is trying to do everything. You just get a very generic function, and then you can try to use other optimization, very mature optimization or auto-diff like libraries. So here I'm using Zygote and Optim. So use Zygote to get the gradient, and then use Optim as the optimizer. And then I even apply this quasi-Newton LBFGS method. And then you basically just optimize it, and then you can basically get a result. And here, this last to the second part, basically, after you get a result, you can reuse this set val function to update it. And then at last, because Quiqbox still has the traditional active and Hartree-Fock methods, you can basically compare results, and they are consistent. So that's I think very related to still pretty related to our kind of like field, which is Hartree-Fock solving. Now, since I'm already treating Hartree-Fock as a generic objective function, then what about I go even a little bit further away? If I just use it for a machine learning task. So here is basically a very simple example of training a multi-layer perceptron. So I'm literally following, because the other day I was like scanning through some machine learning libraries in Julia, and I found that this very popular Lux library, they have this example of fitting a polynomial using a multi-layer perceptron. So basically, this is the result. They have just a 3-layer structure, and then they get a very good result fitting a quadratic function. So we can do the same thing in Quiqbox. So basically, still, I construct a computation graph using those parameters, and then I basically compile them back to some function, and I can train them. And here's the result. We got almost the same. Like I would say, not the perfect fitting, but at least it's doing its job. So conclusions, okay. Quiqbox 0.6 is definitely a much more flexible basis set design toolkit than 0.5 in terms of customizing basis functions and parameterizing them. But 0.6 is also more than a basis set design toolkit. It could be a prototyping toolkit for numerical modeling. The reason I say prototyping is because I'm not mentioning, a very large scale, millions of parameters, because that would require, parameterizations like GPU or like distributed computing. So far, it's just all done on your laptop. It's just for prototyping. It's really for idea exploring. So potential improvement, so better compatibility with parallel computation paradigms and more intelligent decomposition for the integrals, because now you're dealing so many different kinds of basis functions. And then better support with AD, so far only support like Zygote. And also, of course, better integration with other Julia material simulation libraries. I hope so. So finally, acknowledgement. I work closely with my groupmates, Casey Doodle, who's also in the audience. He also gave a talk in the quantum mini symposium yesterday about actually applying Quiqbox to study what is called a type of basis function, Gauss-Lates, for like electronic structure. So check it out. And also I will thank my supervisor, James Daniel Whitfield, who's very supportive of me like doing this very convoluted basis set study, and of course all the members of Whitfield Group and all the funding. So thank you for your time.
Thank you so much, Weishi. Since I know we have lightning talks next, Ray, maybe you want to come set up, and we do have time for maybe 1 or 2 quick questions from the audience.
Hi. Have you considered integrating with the Julia symbolics?
Okay, very good question. Okay, so if you look at, if I remember correctly, if you check the commit history of Quiqbox, back in early 2020s, I tried to use symbolics, but I think at that time era, it was a little bit buggy. So you can see a lot of this code, like the structure of it is very symbolic, like feeling, right? So basically what I end up having is a system that's both symbolic and numerical. So I think maybe in the future I would consider, but for now, like I want to everything like as less dependent on many library as possible. Yeah.
Thank you.
You emphasized how the functionality you've introduced is kind of generic to many numerical problems. Have you considered just breaking out that part as like a lower level package, so that people can use it without having to get all of it?
Yes. I'm actually thinking about just separating the parameterization system, because now it's like so standalone. But I'm just a PhD student after all. I might need to finish my thesis, and whatever comes after that, I will think about it. Thank you.
Anything else? Right. Let's thank the
Thank you.
speaker again.